Hello friends, welcome back. In this video we are going to study the next term used in the coordination chemistry, that is formation constant or the stability constants. So let's start with this. What is formation constant or the stability constant? So we can say that the stability of the complex means whether the complex exists under given or the suitable experimental conditions or not, or we can say that the stability may refer to the action of heat or the light. So based upon this, we are having two types of the stability of the complexes. The first one is which is known as thermodynamic stability, and the second type is the kinetic stability. So we are having two types of the formation constant or the stability constant. The first one is the thermodynamic stability and the second one is the kinetic stability. So let's start with the first one. The first, which is known as thermodynamic stability. So what is this thermodynamic stability? So we can say that this thermodynamic stability, it is a measure of extent of formation of a complex under a given set of conditions at equilibrium. So it depends upon the strength of metal to ligand, that is Ml bond in the complex. Stronger the Ml bond, that is metal to ligand bond, higher will be the thermodynamic stability. So we can say that in thermodynamic sense, the complexes, they are described in terms of stability and instability, right? So this is regarding the thermodynamic stability. So let's move to the second. Second is the kinetic stability. So what is this kinetic stability? It is a measure of rate at which complex formation takes place at equilibrium. Okay. So we can say that it is largely decided by the rate of the reaction and also the reaction mechanism. So in kinetic sense, complexes are described in terms of inertness and lability. While in case of the thermodynamic sense, they are described in terms of stability and the instability. Right? So this is the thermodynamic stability and the kinetic stability. So based upon this, let us find out the terms inert and the labile complexes. So what are the inert complexes? The complexes which exchange ligands rapidly, that is fastly, within a mixing time with the other ligands, are known as the labile complexes. While the complexes which exchange ligands at a slower rate are called as the non-labile, or they are also known as the inert complexes. So we are having the inert complexes which exchange their ligands at slower rate, whereas the labile complexes exchange their ligands at faster rate. So we are having the thermodynamic stability. So in thermodynamic stability of the complex, it depends upon enthalpy change of the reactant as well as the product, whereas in a kinetic sense, or we can say the kinetic stability of the complex, it depends upon the activation energy or the energy of activation. So based upon this, we can say that the example, that is NiCN4 2-. So this example, we can say that it is thermodynamically stable and it is kinetically labile. Whereas the second example, that is a CONH3 3+. This complex, it is thermodynamically unstable, but it is kinetically inert. So this is regarding the inert and the labile complexes. Let's move to the next term. Next term is the equilibrium constants for the formation of the complexes. So let's see that. So consider the aqueous solution of the nickel sulfate. So how this is obtained? We know that most of the complex formation occurs in an aqueous solution. So the aqueous solution of the nickel sulfate is obtained by dissolving nickel sulfate in a water. So we are having the reaction, that is NiSO4, that is a nickel sulfate. It is dissolved in the water and we are getting the aqueous solution of nickel sulfate, which is NaH2O6SO4. Now this aqueous solution of the nickel sulfate is having a particular color and it is green in color. So if you see the solution, this is the solution of the nickel sulfate and this nickel sulfate solution is the green in color. If we proceed further, that means when ammonia is added to this green solution, what happens when ammonia is added? When ammonia is added, these water molecules, they are replaced by the ammonia molecules. So the color change is observed because the water molecules, they are replaced by the ammonia molecule. So we are having the reaction, that is this green solution, which is NaH2O6 2+, in which we are adding the ammonia molecule. What happens? This water molecule, they are replaced by the ammonia molecule. So we are getting the solution. We are getting the complex, that is NaNH3 6 2+. Now this complex is having a color change. Here it is blue in color, right? Why it is blue in color? Because H2O, that is the water, is replaced by the NH3, that is the ammonia. So we are having the solution which is blue color solution. So this is the solution of NaNH3 6 2+. Okay, this color change is simply due to the exchange of the ligands. Now from this we have to find out the equilibrium constant. So how to find out the equilibrium constant? It is nothing but the concentration of the products. Products are this blue color solution and the water divided by the concentration of the reactant, that means this green solution and the ammonia molecules. So we are having the equilibrium constant, that is a K for this reaction, is K is equals to concentration of the products. Product is NaNH3 2+ into H2O6 divided by concentration of the reactant, that is NaH2O6 into NH3 6, and this becomes equals to 10⁸. So this is the equilibrium constant for the reaction. Now here in this reaction we know that this water is used as a solvent, that means it is present in large excess. So we can say that as water is present in large excess, the concentration of the water is considered as a constant. So we have to just remove this water because it is present in large excess. So this equilibrium constant K becomes, K is equals to NaNH3 6 2+. We have to remove, we have removed this H2O divided by NaH2O6 2+ into NH3 6. So this is called as the equilibrium constant. Now here this K is called as the stability constant, and the inverse means 1 by K is known as the instability constant. So this is called as the equilibrium constant. Then for the types of formation constant, so formation of the complex may take place slowly if ligand molecules, they are added slowly, right? So based upon this, the reaction may proceed in steps, or the reaction may proceed in steps, and hence the formation constant may be described as a stepwise formation constant, which is called as a K, or secondly overall formation constant. So there are two types of the formation constant. The first one is the stepwise formation constant when the ligands, they are added slowly, or second is the overall formation constant, that is beta. So let's study these two one by one. So we are having the first type, that is the stepwise formation constant. So when this stepwise formation constant occurs, when the ligand molecules, they are added slowly, that means a complex formation occurs in a steps, one to many steps. So let's take a general example. The metal complexes are formed in solution by stepwise reaction as, so we are having the metal and a ligand, one metal and a ligand. They gives the formation of a complex, that is Ml, right? So the constant, therefore the constant K1 is equals to concentration of the product, that is Ml divided by concentration of the metal and the concentration of the ligand. So this is the constant K1. Now in this Ml, that is the product, we have again added one more ligand molecule. So we are having the Ml plus ligand, right? So we are getting the product as Ml2. Therefore the constant will be K2. K2 is equals to concentration of product, that is Ml2 divided by concentration of Ml into L, that is the reactants. So this is known as the K2, the second constant. Now in this product, that is the Ml2, we still added one more ligand molecule. So it becomes Ml2 plus L. So the product becomes Ml3, and therefore the constant is K3, and K3 is equals to concentration of the product, that is Ml3 divided by concentration of the reactant, that is Ml2 into L, right? In this way, we can add n number of ligands. So it becomes Ml n minus 1 plus L, and hence the product becomes MLN. N means the main number of ligands, and therefore the constant is Kn. Kn is equal to concentration of MLN divided by concentration of reactant, that is Ml n minus 1 into concentration of the ligands. So in this way we are having the number of constants, that is K1, K2, K3 up to Kn. So let us take an example. That is the formation of the silver AgNH3 twice plus by stepwise reaction, which is represented as, so first of all we are having the Ag plus, that is the metal, plus a ligand, that is the NH3, one metal and one ligand. So we are getting the formation of the product. Product is AgNH3 plus. So we can say the K1, that is the constant, is equal to concentration of the reactant, that is AgNH3 plus divided by concentration of the product, that is Ag plus and NH3. Now in this product we have again added one more ligand molecule. So it becomes AgNH3 plus NH3. So the product becomes AgNH3 twice plus, and hence we are having the constant, that is a K2. K2 is equal to concentration of product, that is AgNH3 twice plus divided by concentration of reactant AgNH3 plus into NH3, right? So here in this way we are having the n number of products. So here K1, K2, K3 up to Kn, they are called as a constant, and here they are stepwise formation or the stability constant, right? The ligand molecule, they are added slowly, or we can say the ligands, they are added in steps. Therefore it is called as the stepwise formation or the stability constant. Now let us start with the second type, that is the overall formation constant, and this overall formation constant, it is represented by the symbol beta. The overall formation constant, that is capital K or beta, is the measure of extent of association of metals and the ligands. The overall formation constant, that is a capital K or beta, it is related to stepwise formation constant K1, K2, K3 up to Kn, as K, that is a capital K or beta, that is the overall formation constant, it is equals to K1 into K2 into K3 up to Kn. That is B1 is equals to K1, B2 is equals to K1 into K2, B3 is equals to K1 into K2 into K3, etc. So let us explain this by taking an example. So for the formation of AgNH3 twice plus, the overall formation constant, that is capital K or beta, it can be given as B1, that is the beta 1 is equals to concentration of the product, that is AgNH3 plus divided by reactant, that is Ag plus into NH3. Okay. Similarly, we are having the second, that is the beta 2, which is equals to AgNH3 twice plus divided by AgNH3 plus into NH3. So this is from the second reaction. Now let us correlate this with the stepwise formation constant, that is we can say that B2 is equals to AgNH3 twice plus divided by AgNH3 plus into NH3 into, it is equals to AgNH3 plus divided by Ag plus into NH3, right? So simply we can say that it is equals to K2 into K1. We may refer to the earlier reactions, right? That is, we can say that B2, that is beta 2 is equals to K1 into K2, right? So therefore Bn is equals to K1 into K2 into K3 up to Kn. Hence there is the same number of overall formation constant as the stability formation constant. So this is a correlation between the stepwise formation constant and the overall formation constant, that is small k and beta. Let us move to the next point, that is the factors affecting the stability of compounds. So how many factors are there which affect the stability of the compounds? So we are having the stability of the compounds. So the stability of the compounds depends upon the three factors. The first factor is the nature of central metal atom or the ion, right? This is the first factor. The second factor is the nature of ligand, right? And the third factor is the chelation. So these are the three factors on which the stability of the compounds depends, right? Further, we can say that this first factor, that is the nature of central metal atom or the ion, it depends upon the again two. The first one is the electronegativity of the metal ion, and the second one is charge density. So these are the two factors which depends upon the nature of central metal atom or the ion. Further, the second factor, that is the nature of ligands, it again depends upon the two factors. The first one is size and charge on ligand, and the second is the basic characters. So these are the various factors on which we can say that the stability of the compounds depends. So let us study these various factors. So first factor, out of the three factors, the first one is the nature of central metal atom or the ion. We have seen that it depends upon the two factors. The first one is the charge density, and the second one is the electronegativity of the metal ion. So let us take the first one, charge density. What is the charge density? Charge density is equals to charge on the metal ion divided by radius of the metal ion. This is the charge density. That means we can say that this charge density is inversely proportional to the radius of the metal ion, right? So greater the charge and smaller the size of the metal ion. Greater the charge and smaller the size of the metal ion means greater will be the charge density, and hence the resulting complex will be the more stable. So it depends upon this charge density, which is equal to charge on the metal ion divided by radius of the metal ion. Thus we can say that metal ions of small size and greater charge, they are the stable complexes. Then the second, that is the electronegativity of the metal ion. Metal ions of equal size but with a greater charge, they offer strong electrostatic force of attraction and hence brings the ligands closer, and hence they are forming the strong bonds, right? So we can say that the example, the size of Fe3 plus ion is smaller than Fe2 plus ion, right? Fe3 plus is smaller in size than the Fe2 plus ion. Hence we can say that Fe3 plus ion is more electronegative than the Fe2 plus ion. As a result, the complexes formed by the Fe3 plus ions are more stable than the Fe2 plus ions. Let us see their structures. So we are having this Fe2 plus ion. This Fe2 plus ion is having the radius 0.63, whereas the second one is the Fe3 plus ion, which is having the radius 0.49. That means we can say that this Fe3 plus ion is smaller in size than the Fe2 plus ion. So we can say that the complexes formed by Fe3 plus ions are more stable than the complexes formed by the Fe2 plus ion. So this is regarding the first factor, that is the nature of the central metal ion or the atom. So let us move to the next one. The second one is the nature of the ligands. Ligands means the coordinating groups or the groups which are attached to the central metal atom or the ion. Again, it depends upon the two factors. The first one is the basic character and the second factor is the size and the charge on the ligands. So let's start with the first one, that is the basic character. So the ligands with the strong basic characters, they have greater tendency to donate the electrons, right? So we can say that the resulting complexes will be more stable when they are having the more basic characters. Thus, greater the basic character of the ligand, more will be the stability of the complex, right? Then, the second is the size and the charge on the ligand. So smaller the size and greater the charge on the ligands. That means the greater the charge density, there will be the stronger metal to ligand bond, and hence there will be the higher stability of the complex. Hence, let's take an example. The complex is formed by the F minus ions. They are more stable than those of the Cl minus ion. This is just related to this one. This depends upon the smaller the size and greater the charge on the ligands. Stronger is the Ml bond and higher is the stability of the complex. The third, that is the chelation. The third factor which affects the stability of the compound is the chelation. That is the formation of the complex by using the chelates or the chelating ligands. So chelating ligands means the bidentate or the polydentate ligands. They form more stable complexes than the monodentate ligands. Why this is so? Because they are having the more donating groups or donor atoms. Therefore, they are forming the stable complexes. So in chelate complexes containing 5 and 6 membered rings are more stable. Right? So its example is NiEN thrice 6 2 plus. En means ethylene diamine. Right? It is having 2 nitrogen atoms. That means the 2 donor atoms. And these 2 donor atoms, they are forming a ring. Right? So it is more stable than NiNH3 6. Why? Because this NH3 6 is the monodentate ligand, whereas this ethylene diamine is the bidentate ligand. So this is because En is the bidentate ligand and it forms a ring, whereas ammonia is the monodentate ligand and it does not form a ring. Therefore, hence we can see that the complexes formed by using the ethylene diamine, they are more stable than the complexes formed by using the ammonia. Thank you. So this is regarding the formation constant or the stability constant.